welcome back. And so the last two techniques are unrelated to one another, but they're a little bit more esoteric. I thought I would mention them though. The first one is magnetic susceptibility, and I've talked about magnetic behavior. Well, this is how you would actually measure it. Well, is how you would actually measure it 30 years ago, but it's easier to understand than the modern technique, which I'm going to talk about in a second. Right? So if you want to measure magnetic behavior, you have to measure the interaction of your sample with a magnet. And if your sample is magnetic, a magnet will either repel or be attracted by your sample, right? And so in this technique, what we have here is a sample that can be lowered into a magnetic field where the magnet is on top of a balance, right? So when you raise the sample out of there, there's no interaction. You're just measuring the magnet. But as you put the sample in, well, the magnet will either appear to be heavier or lighter because your sample is either repelling or attracting to the magnet, right? So you can measure the magnitude of that interaction by measuring how much the sample affects the effective mass of the magnet. Remember, you're not actually changing the mass of the magnet, you're just changing the measurement of it because the sample is interacting, right? And that's pretty much all I'm going to really say about how that particular technique works. And as I said, you can calculate a magnetic moment based on the spins. So this is a different form of that equation. S times S plus 1, the square root of that, times G. And G for free electron is right around 2. So the formula I think I gave you, I don't actually remember which one I gave you in class. It might have used N's for, and then you didn't have the G, but regardless, for free electron, G is about 2, and you end up with exactly the same equation as you did in that case. Right, and so you compare the measured value of magnetic moment to the calculated from just the spins. And so you can tell how many unpaired electrons you have in your sample, and whether it's high spin or low spin, whether there's something odd going on, because sometimes you get a higher value than these numbers, sometimes you get a lower value. The new modern technique for measuring it is called, well, it's called magnetic susceptibility still, but the device is called a SQUID, or superconducting quantum interference device. And this is the reason why it's used now, is that it is way more sensitive. It's incredibly sensitive. This technique can measure fields as low as 5 attotesla. That's 5 times 10 to the minus 8th Tesla. Typical refrigerator magnet has 0.01 Tesla, so that's 16 orders of magnitude smaller, right? That's an incredibly small magnetic field. The problem is that it requires a superconducting material, and most superconducting materials only superconduct at ultra low temperatures, so below 4 degrees Kelvin. And so this device requires that it be immersed in liquid helium at 4 degrees Kelvin. So we're not going to have one here at Pacific. The way it's really cool though how it works. And so you basically make a circuit out of the superconducting material, but then you put a really thin insulator in, so it's actually not connected. And this insulator is thin enough, it basically has to be thin on the atomic scale, right? So maybe nanometers thin, so that the electric field can actually reach across here. And then you put a little biasing current, you put a little tiny voltage across this. And it's small enough that electrons can't jump across this gap because there's an insulator there. But a weird thing happens is if you take a magnetic material and pass it through this hole, what ends up happening is that the magnetic field interacts with the electric field here and causes electrons to hop over this gap. And it's a process called tunneling, is that the electrons don't travel through, they actually hop over. So they just skip it. It's a weird phenomenon called tunneling. And you pass the sample through, they hop over. You pass it back the other way, they hop the other direction. And so you just pass it up and down, up and down, up and down, and measure the current going back and forth, back and forth, back and forth. And the number of electrons that hop over, or the current that you generate, is proportional to the magnetic field in your sample. If you have no magnetic field for your sample, no electrons are going to pass. If it's weak, a few electrons will pass. If it's strong, more electrons will pass. So you can correlate the current with the magnetic field in your sample. Really cool technique. Tunneling. So the last technique I want to talk about briefly is a technique called Mossbauer spectroscopy. And one of the reasons why I want to talk about it is that it's a little bit bizarre. And it's a technique that actually measures absorption due to nuclear transitions. Right, so we've talked quite a bit about electrons hopping from one energy level to another, from one orbital to another, right? And that corresponds to, visible electrons for DD, for these valence orbitals, right? That's usually UV, from popping from a valence orbital off the molecule. Core electrons being promoted by X-rays. Right? Those are all electronic transitions, an electron hopping from one energy level to another, or one energy level to off the molecule. Electrons moving around. Well, nucleuses also have energy levels. It's not something we ever really talk about in chemistry, but this Mossbauer technique is based on transitions between nuclear energy levels. You can have ground state nucleus and excited state nucleus. And because nuclear energy, the interaction between nucleons and the nucleus is much stronger than the interaction of electrons, the difference in energy between nuclear energy levels is much higher. And so this technique uses gamma rays in order to look at these transitions. Now, it turns out it's really hard to get a source of gamma rays. And so what you do is you get a radioactive source. So in this case, the sample is iron. We start with a radioactive source of cobalt, and that cobalt decomposes to an excited state of iron, and that iron then gives off a gamma ray when it decomposes. And you use that as a source of gamma rays to shine at a ground state iron sample. And so you have gamma rays produced by iron hitting an iron sample. And some of those photons, which are gamma rays, will be absorbed by the nucleus and get promoted up to a higher nuclear energy state. Right? So in theory, the photons given off by this iron should be exactly the same energy as the photons that your source absorbs. Right? Because they're both the same nucleus, they both have the same kind of energy levels in the nucleus, and so the photons given off by your source should be exactly the same energy as the photons in your sample. But it turns out that the nucleus, the nuclear energy levels, are really tiny, slightly affected by the chemical environment that the iron is in. And so the energy levels, the nuclear energy levels in iron metal will be just slightly different than the nuclear energy levels in hexaquo iron. And they'll be slightly different than the energy levels in like a porphyrin, like in hemoglobin, iron in hemoglobin. Right? It'll depend on oxidation state, iron 2 plus, iron 3 plus, iron 0, iron 4. It'll depend a little bit on the geometry as well. Right? But it's a really tiny difference in energy. In fact, I think it's something like 1 part in 10 to the 18th or something like that. Like really fractional, like incredibly small amount of energy difference. And the way that that energy difference is detected is really cool, right? How do you match the energies, right? You have to somehow manage to scan the energy of your source with the energy of your sample, because unless you use exactly the same material, it's going to be at a different energy, and you can't modify the energy of the source. So how do you actually get the energies to match up? Because they're going to be different. The way they do it is by using the Doppler effect. You take your sample and put it on a little tractor and move it back and forth. And when it's moving towards the sample, right, the frequency is higher for the photons, and so that's higher energy. And when it's moving away, it's lower energy. And if you want to look at a broader range, you have to move it faster, or a more refined range, move it slower. So you actually use the Doppler effect to modify the energy difference between your source and your sample. Okay, so the key parameters that are measured, this is termed out isomer shift. That's the position of the peaks, right? So it corresponds kind of to chemical shift in NMR. And then the splitting, right? Sometimes the peaks will be split, and that tells us about the symmetry of the environment. So the magnitude of the splitting tells us about the symmetry. Turns out highly symmetric things have small splitting, asymmetric things have bigger splitting. So it's not like NMR, in that in NMR, the splitting tells us about neighbors. Here, it's telling us about symmetry, because it's a different mechanism. Right, so this kind of gives the isomer shift scale for iron. And so iron 4 compounds will show up way out there for if they're spin of 1. Iron 4 with spin of 2 will show up in there. Diamagnetic covalent compounds will show up there. Things out here, iron 2, spin of 2, iron, I can't even read that one because my thing's covering it, right? So you can see there's a lot of overlapping ranges. So this technique, you might get lucky and see a shift that's in its own kind of region, and then you can clearly identify it. But a lot of times you'll see peaks in region where you have a lot of overlapping stuff, right? And so you could, for example, use this to determine whether you have iron 2 that's in spin of 2 or spin of 1, because they're in different places, but only if you know that it's iron 2, right? If you don't know that it's iron 2, there's going to be a lot of things that are overlapping for this region, right? So it's a technique that you kind of have to have other information about the system for it to give you useful information usually. Right, so this shows kind of what the Mossbauer spectra would look like, and this is for a couple of different iron 3 compounds, where you have iron 3 linked by an oxygen bridge, and then each of these irons is linked to these other ligand donors. And I left off kind of the rest of the stuff. They're just organic molecules that are donating these. Didn't really matter, right? So it's 6-coordinate iron 3 plus, 6-coordinate iron 3 plus, and then an oxygen there. And it turns out the oxygen bridge forms a really short bond with the iron. And so this is a pretty asymmetric environment. Even though it's octahedral, you have 1 short bond and then 5 kind of normalish bonds. And so it's an asymmetric environment, and you get a fairly big splitting between the two peaks in the Mossbauer spectrum. You'll notice, and then you can take exactly that compound and protonate it, right? Because this oxygen is somewhat basic, and so you can add acid and protonate it. So you haven't changed anything about the rest of the ligands around it. You've just protonated that. And you've turned that from a 2- ligand into a 1-. And so what happens is that the bond there actually gets longer. It becomes comparable to these other bonds. And so the environment now, actually, you have all relatively equivalent bonds. It's a more symmetric environment, and so the splitting drops down. You get a smaller splitting. And you'll notice that both of these are in almost exactly the same, right? The chemical shift is right at the middle of the two peaks, where it'd be the average of these two peaks, right? So the chemical shift or isomer shift right there and right there, they're almost identical because the iron is in this is 6 coordinate, high spin, and it's iron 3+ in both cases. Right? So the shift doesn't really change much, it changes a teeny bit, but what's more striking is that the splitting pattern is changed. And I'm including data on this second compound. This is a trimer of iron, where you have 3 iron ions in a triangle. There's an oxygen in the center. These are acetate ions that actually bridge on each of the sides. So 2 bridges on one side of the triangle, 2 bridges on another side, 2 bridges on another side, and then water sticking on the outside. And if you count up the charges here, you'll find out that the iron, there has to be 8 positive charges split between these 3 irons, so it's not divisible. And so it looks like there are 2 iron 3+ and 1 iron 2+ ions in this. It's called, and so that's an example of a mixed valence compound. And so when you measure the Mossbauer spectrum of this at high temperature meaning, well, a little bit, I guess 290 K is room temperature, all you see is a single peak in the Mossbauer spectrum. Right? So that means that at room temperature, all of the iron ions are equivalent, even though you know that there are only enough electrons for 3+, 3+, and 2+, but you measure the Mossbauer at room temperature and you see just one environment, right? So that means that the electrons are moving around too fast to detect. You cool this down, you start to see kind of a splitting of the pattern. You start to resolve not just one peak, but multiple peaks. And by the time you get all the way down to 17 Kelvin, you see now 3 different distinct peaks. And the interpretation of this is that, oh, there are 2 environments that are both split into the doublets. So iron tends to form doublets in Mossbauer spectroscopy. And so we would expect to see a doublet from the iron 2+ and then a doublet from the iron 3+. And the doublet from the iron 3+ should be twice as intense. And so this is overlapping doublets. You have a large splitting for the low intensity one. And so one of the peaks is here, and then one of the peaks is over here. And then the small splitting is over here, right? A splitting pattern like that. So you get 2 there. So it's like they're overlapping kind of like that. And so you get one that has intensity of 3 because the peak for both this couple and this couple is there. And then a 2 to 1 because this is the iron 3+ and this is the iron 2+. And so it looks like the iron 2+ is a much more asymmetric environment than the iron 3+. And if you think about the electronic structure, iron 3+, D5, it's high spin, 1 electron in each of the orbitals, that should be pretty symmetric. The iron 2+ has 6 d electrons, and so there'll be 4 electrons in the lower T2G level, and so that's going to be subject to Jahn-Teller distortion, and so it's a little bit distorted. You can actually detect that in the Mossbauer spectrum. So the examples I've used here was iron, but you can use this technique with other elements. The limiting factor actually is the source, right? Where do you get a source of gamma rays? And so you have to have a source, a radioactive source of that element that actually produces those gamma rays in order to use this technique, right? And so other elements that you can do this with are tin. I think tin is the next most common element that it's used for. And then iodine, you can use it. Iodine is important for maybe for some medical applications, because one of the nice things about this technique is it's very specific for that element, right? You can look at an element in a pretty wide, a big mixture, and just pick that particular element out. Right, and so for just including this for completeness, this is all data for tin, and it lists kind of the range of chemical shifts that you would expect for tin. So everything from tin tetrafluoride with negative 0.47, negative 0.48 for these really electronegative things on there. As you put less electronegative elements on the tin, it goes to higher isomer shifts. Right, so you can maybe get the idea of, you get a range of things. And there are some patterns, but and if you were into this kind of thing, you could interpret and identify compounds or guess at what ligands would be attached to the tin. So I think that's it for today. I guess I will do one last technique as a little bonus, just because I like it. But we'll stop this recording and then come back.